This is the second lecture on chapter 16, which deals with substitution reactions at acyl. The key word here is acyl carbons. That's carbon that have a carbon-oxygen double bond. So in this presentation, we'll do a quick review of acyl substitution reactions. Then we will go into a specific acyl compound, esters, and we'll look at specific reactions. The first is the reaction with water. The next is a reaction with ammonia and amines. And we'll also look at the reactions with organometallic reagents as nucleophiles, hydrides as nucleophiles, and enolates as nucleophiles for these reactions. Lastly, we'll look at substitution reactions that's applied to synthesis. Okay, so as a quick review, last lecture we looked at alkyl chlorides or acid chlorides. And we said that these compounds are very reactive. They are very reactive because the carbon, here's the acid chloride down here, so the carbon that is electrophilic is bonded to an electronegative oxygen, which makes this bond here a polar covalent bond. In addition, it is bonded to a Cl, which is also electronegative, and equally important, this is the leaving group. So it has a very good leaving group as shown here. How do we know that it's a good leaving group? We know that it's a good leaving group because the conjugate acid of Cl minus is HCl. The pKa here is minus 7.3, which means that it is a very strong acid. As you may recall from your Gen Chem, that the acid-base relationship, the conjugate acid-base relationship, is a strong acid gives a weak conjugate base. So therefore this is a weak conjugate base here, which means that it is very stable, and which means that it is a good leaving group. So acid chlorides, as we said in the last lecture, they are extremely reactive, extremely reactive. Let's look at another compound here, and this is the anhydride, which we briefly introduced last lecture. Here is the key. This is the electrophilic carbon, and a nucleophile can react here, which makes this the leaving group. As you can see from the mechanism, here is the leaving group leaving, and this is the leaving group, which is the carboxylate anion. The question now is that a good leaving group? And to determine if it's a good leaving group, we can determine if it's a weak or strong base. It is a weak base because its conjugate acid, carboxylic acids, they have pKa's in the region of 4.7, which means that this is a pretty strong acid, not the strongest of acids, but it's a fairly strong acid, which means that this is a good leaving group. Not as good as the chloride anion, so therefore these compounds are not as reactive as the acid chlorides, but it is still a fairly good leaving group, and anhydrides are fairly reactive compounds. Let us turn our attention now to the esters. Here's an ester. And so the substitution reaction now would involve the nucleophile replacing or being substituted with the OCH3, or substituting the OCH3, which means that the OCH3 here would be the leaving group, which would be the methoxide anion. The question now is that a good reaction? Is that a favorable reaction compared to the other two? As you can see here, the methoxide anion, its conjugate acid is of course the alcohol. The pKa of alcohols are, especially methanol here, is 15.7. As you can see from that number, that is a weak acid. If it's a weak acid, that means that its conjugate base here is a strong conjugate base. Of course, you know that because you use that whenever you do an elimination reaction. You need a strong base. So this is a strong base, which means that it is a very poor leaving group. So this reaction here is not favorable because the leaving group here is a poor leaving group. Let's see what can be done, however. In the presence of an acid, protonation of the carbonyl occurs, as you can see here. And of course this carbon here is electrophilic, and we can draw resonance structures to show that this carbon here is electrophilic or partially positive. So in the presence of an acid, an ester, as we have seen here, will protonate to give this as our electrophilic carbon. The nucleophile can now attack to give a tetrahedral intermediate, same as we had before. However, since it is in an acidic medium, protonation can occur on this group here to give this protonated alcohol. This protonated alcohol can then leave, so that's our leaving group, it leaves as an alcohol. The question now, is this a good leaving group? Let's do the analysis. The conjugate acid of this leaving group is the protonated alcohol. The pKa of a protonated alcohol is minus. Notice again, minus, negative. That means it's a strong acid. If it's a strong acid, this is a weak base. A very weak base, in fact. So therefore, this is an extremely good leaving group. Of course, once you have this, it's just a matter of losing this proton here to give your product, which means that the acid here is really a catalyst because it's used and then regenerated. Bottom line, an ester is unreactive in just a neutral medium, but once an acid is introduced, it becomes reactive because it produces a good leaving group in the form of an alcohol. Let us look here at a specific reaction. This one is the reaction with water. So we're substituting here OH for OCH3. Substitution at an acyl carbon. As we said, these reactions proceed in the presence of the catalyst, so we say it's acid catalyzed. In the presence of an acid, this oxygen here is protonated as shown here. This carbon is electrophilic. Here's our nucleophile. These electrons bond here to give this species. This proton is lost to give our tetrahedral intermediate here. In the presence of the acid, however, a protonation of the OCH3 occurs to give this. This now becomes the good leaving group because it will take these electrons to form our neutral alcohol, which is an extremely good leaving group, and what's left behind is a carboxylic acid. So the bottom line is esters in the presence of water and an acid as a catalyst will give a carboxylic acid and alcohol as the product. We call that hydrolysis, an hydrolysis of an ester. Hydrolysis because of hydro, water. Here's another example. Here's an ester, this time reacting with an alcohol. So we have here a substitution of OCH3 with the alcohol. So we don't have the mechanism here, but as you can imagine, these electrons will attack here, and of course there's an acid, so this will be protonated, and it keeps going until the final product is this, where this group here is coming from our alcohol. And of course the methanol is coming from the leaving group. So that's the product. Acid catalyzed reaction of an ester with an alcohol. These reactions are called transesterification because, as you can see, this is an ester in the reactant and this is an ester right here in the product. But it's a transesterification because we're exchanging this OR group for this OR group. Here's another example. This ester, this alcohol. So here's the group that will be substituting for this group right here, and this group right here will of course form the alcohol, and this group here will form the ester. That's called transesterification in the presence of an acid. One thing I should point out though is that these reactions here are reversible. So if you want to produce this reaction going to the right to produce a lot of this as the product, you can use Le Chatelier's principle as you studied in your Gen Chem by removing the reactant, hence the equilibrium will shift to the right. So if you can find a way to remove methanol as it's produced, the reaction equilibrium will shift to the right, and this will be the product. You can shift the reaction to the left if you can find a way to extract the reactant so it shifts. So that's Le Chatelier's principle. Let's look here at a molecule that's difunctional, polyfunctional. It has an ester functionality here, and it also has an alcohol functionality on the same molecule. As you can imagine, here's a nucleophile, here's an acid, here's an acyl group, and this is a potential leaving group. So the reaction will occur to give a cyclic ester. The term for that is, another term for that it's a lactone. And of course we have our leaving group as the alcohol. So here's a more specific example, nucleophile right here in the form of the alcohol, ester right here. So the reaction will occur, this will be our leaving group here, and of course we have a cyclization here to give this lactone as our product. As you can imagine, the same type reaction can occur with amines. So here is a primary amine, methylamine. It's nucleophilic because it has an unshared pair of electrons. In an acid or acid catalyzed, you can imagine this OCH3 will leave and this nucleophile will attack that carbon to give here this type molecule now known as an amide. So here is the amide bond. So this is called known as a secondary amide because it has two groups, alkyl groups bonded to that nitrogen. The leaving group here is methanol, as you can see here. Same type reaction here. This is a secondary amine, leaving group, nucleophile, acid catalyzed, amide product, and our leaving group as methanol. So let's look at the mechanism here for the acid catalyzed reaction with ammonia. Excuse me. So here's the ester. In the presence of an acid, protonation will occur here, as you have seen. This carbon is electrophilic. These electrons can attack to give this tetrahedral intermediate. Because it's in an acid medium and it's an acid catalyzed, we can lose a proton here to give this, and then the proton can go over to here to give this. As you can see, here is our leaving group, alcohol, ROH. So that's minus that. We know that that is a good leaving group to give this protonated amide. Loss of the proton will give the amide. As you can see, this proton here is in fact a catalyst because it is used here and regenerated here. So by definition, again, a catalyst is a molecule or substance that's used in a reaction but not consumed. Here's a reaction as a very similar reaction to the reaction with alcohol, but in this case it's an amine, primary amine right here. Here's the ester, so cyclization will give here the lactam. This is an E, a lactam, and we have here lactam. So we have here the cyclic amide. So you can see once again these electrons here will react here, and this will be our leaving group as a methanol, and this will be our cyclic amide. Let's turn our attention now to the reaction with a Grignard reagent. As you know, the Grignard reagent is a very useful reagent in organic chemistry, and it's really RMGX, where R is an alkyl group, but the key here is it's CH3 negative and MGX positive. So this CH3 here is the nucleophile. It can come in here. This will go to form the ketone. As we have seen with the reaction with the acid chloride, the ketones react readily with another mole of the Grignard to give the salt, and of course after hydrolysis gives the tertiary alcohol. So once again, just to make sure you got it, this is a Grignard reagent, CH3 negative. It reacts here. That leaves to give a ketone. The ketone is very reactive with a Grignard, so another mole, that's why we have an excess here, will react with a ketone after hydrolysis gives a tertiary alcohol. Notice again that these two groups are the same because they're coming from an excess of the Grignard. Let's look at this one, however. This is the Dieckmann reagent. It's bonded to copper, so it is not as reactive. This is not as nucleophilic, the CH3 negative. So it will react here at the electrophilic carbon. This will leave as methanol in our acidic workup, and it will stop at the ketone. So here you have a strategy to go from an ester to a ketone, or you can go from an ester to a tertiary alcohol with two groups here are the same and coming from our Grignard reagent. Let us look at this one. As you can see, here's a similarity. You know that lithium aluminum hydride is very reactive. It produces H minus. That's the nucleophile. So H minus will come in here, and this will leave as, of course, our methanol, and after workup you will, well, before workup you'll get your ketone, your aldehyde, pardon me, and of course a second mole will give us our primary alcohol. Let's review that just to make sure we have it. So the first mole of H minus will come in here, and that will leave, and we'll have here an H, which is an aldehyde. But because this is so reactive, another mole of H minus will come in, and after workup with water will give us a primary alcohol. So these two H's are coming from lithium aluminum hydride. We need not write an excess here because lithium aluminum hydride has 4 moles of H minus. Let's look at this one. This is triterbutoxy aluminum hydride, methoxide aluminum hydride. So here it's not as reactive, with just 1 mole of H minus compared to lithium aluminum hydride. And of course, as you can imagine, the H minus, let's see if we can write that here, will come in right here, and this will leave to give us the aldehyde. So again, you have a strategy here. If you can go from an ester to an primary alcohol, 2 hydrogens coming from lithium aluminum hydride, or you can go from the same ester to the aldehyde, with just 1 mole of H minus coming in, but we'll have to use a specific reagent here. Specific reducing reagent. So let's see if we can solve these problems here, these questions. So the question is, wherever there's a question mark, put a reagent. So your analysis will include looking carefully at the reagents that are given. So here's lithium aluminum hydride tertbutoxide. 1 hydrogen, not a very strong reducing agent, but it will give up 1 mole of H minus as our nucleophile. Here it is. So what goes here more than likely is an ester. But it looks like this. Here is aluminum hydride, strong reducing agent, 4 moles of H minus. Here's an ester. So you can imagine this will be a primary alcohol where we have 2 moles of H minus being delivered to this carbonyl, and this leaves. Cuprate, Dieckmann reagent, not as strong as the Grignard. So therefore this is an ester, and here is our methyl group coming from our Dieckmann reagent. Here is a Grignard reagent, very strong reducing agent, and it's in excess, so we have 2 moles or as many moles as needed. And here's our leaving group, so we can react here and do it twice to get 2 moles here, and after workup we'll get a tertiary alcohol. So as it's not surprising, here's our ester, weak reducing agent, aldehyde. Stop at the aldehyde. Lithium aluminum hydride, strong reducing agent with H minus, 2 moles. Because it's very strong, this leaves to give a primary alcohol. Here's our Dieckmann. Here's the nucleophile. Weak reducing agent because it's bonded to copper, not as hard as your magnesium for the Grignard. So therefore it will just introduce one of the methyl group here for the substitution reaction. The analysis of this one, here's our Grignard, methyl, excess, leaving group. So we can expect this to come in to give the ketone initially, and a second mole to come in reacting with the ketone, and after hydrolysis gives us the tertiary alcohol, where this group and that group are coming from the Grignard reagent. That's going to be key for the synthesis that we'll do in the last slide. Let's look at another type nucleophile. This one is called the enolate. So molecules, esters, that have a alpha carbon. This alpha carbon, if it has hydrogens, they're called alpha hydrogens. They are acidic. So we have an acid-base reaction here. So here is our strong base. It can abstract one of those hydrogen as a proton to give here the alcohol, but most important, it gives here a enolate. It's a nucleophile because it leaves behind its bonding electrons from the proton. So this is a nucleophile. So it's a nucleophile, also called an enolate of an ester. As you can imagine, this ester here, which is the enolate of the ester, can now react with an ester, where this leaves to give a new molecule. And of course, this is the leaving group, leaving as our alcohol. So this is called a beta keto ester. Why beta? This is the alpha carbon, this is the beta carbon, and it has a keto group. So let's go over this one more time just to make sure we got it. If you have an ester, add a strong base to that ester. If that ester has an alpha hydrogen, it will deprotonate, just taking off the hydrogen and leaving the bonding electrons here. This is called an enolate of an ester, which is also a nucleophile. So here's the nucleophile. This nucleophile can react with an ester to produce a new molecule called a beta keto ester. This type reaction was discovered by Claisen and is now known as the Claisen reaction. That's the Claisen reaction. So let us look at the Claisen reaction with another type molecule. So let's assume that we have created the enolate of an ester. Here it is. So this enolate of the ester, if we introduce another ester, notice this ester does not have any alpha hydrogens because this is the alpha carbon, but there are no hydrogens bonded to that carbon. So this enolate will react here, and this OH will leave as ethanol, and we have our beta keto ester as shown here. Notice we're making some really larger molecules here by reacting some smaller components. This reaction, because we are reacting an enolate with a different ester, it's called a crossed Claisen condensation or a crossed Claisen reaction. Here is another reaction, and this is the intramolecular Claisen. So as you can expect, here is an ester, here is an ester, in the presence of a base right here, sodium ethoxide. It will pull off one of these hydrogens, because this is the alpha hydrogen here, carbon, and here's the alpha carbon. So it can pull off one of these, and the mechanism is actually on the next slide, but the product is actually this. Looks surprising, but let's see how that is formed. As I mentioned earlier, this is the alpha carbon because of the ester right here. This is another alpha carbon because of the ester right here. So in the presence of a strong base, it can pull off one of these hydrogens as a proton, leaving behind these electrons here. That's nucleophilic. So it can do an intramolecular reaction here to give this as a tetrahedral intermediate. These electrons can come back in as shown here, and this leaves as our ethanol to give this as the product. Let's make sure we have the correct size for the ring. So this is 1, 2, 3, 4, 5, and 6. So that's a 6-membered ring that is formed. So again, you may want to count your carbons just to make sure you account for all the carbons in that reaction. This type reaction, an intramolecular Claisen, is known as a Dieckmann condensation. So we have lots of names here. So the Dieckmann is really a Claisen, but an intra to form a ring. The Claisen is a reaction between a enolate and an ester. The crossed Claisen is between an enolate and an ester that does not have an alpha hydrogen. Let us take this reaction a bit further. So the product that we just made was a beta keto ester. Why a beta keto ester? As we said, this is the alpha carbon and this is the beta carbon because we're talking about an ester. So the first and second beta keto ester. So here is an ester right here. So it has a potential leaving group here. Here's an acid as a catalyst. Here's a nucleophile water. So you can expect this reaction to go as a substitution to substitute the OC2H5 with the OH to give ethanol as a leaving group and substituting our OH right here. So this is another substitution reaction, hydrolysis, where we have substituted the OC2H5 with the OH from water. This molecule is called, as you can imagine, a beta keto carboxylic acid, alpha and beta keto. Very reactive. In the presence of heat, it decarboxylates, giving off carbon dioxide to form an enol. Just follow these arrows here. You'll see carbon dioxide coming off right here. And an enol. Of course, as we have discussed from previous lectures, the enol is not as stable as the keto form, so we have a keto-enol tautomerization. So this becomes our final product. So again, we can go from this ester into this ketone by this set of reactions. So let's do a quick summary before we look at some applications. So the ester is a very common organic molecule, used a lot for starting material, fairly cheap. So it's a good starting material for the synthesis of a lot of compounds. Not as reactive, however, as the acid chlorides and the anhydride, but in the appropriate catalyst, they will react. So let's look at this one. Let's start here. This is the hydrolysis. We'll give carboxylic acid, aluminum hydride, strong reducing agent, will give us the primary alcohol. Amines and ammonia will give us the amide because we're substituting here the OR for the NH2. The carboxylic acid or the carboxylate anion, substitution here will give us the anhydride. If we react this with the enolate, it gives us the beta keto ester, as we have seen before. Notice again that this beta keto ester can undergo other reactions such as hydrolysis here and decarboxylation, as we have seen in the previous slide. This is the Dieckmann reagent, so it gives a ketone and stops. This is the very crowded and less reactive hydride. Here's the H minus, so it stops at the aldehyde. And here is the good old Grignard, very reactive, and it gives us 2 R's to give us a tertiary alcohol after hydrolysis. Why? Because the Grignard is very reactive. So once the ketone is formed in the initial step, the ketone reacts with another mole of the Grignard, that's why we have an excess here, to give a tertiary alcohol. So as you can see, we have lots of applications for the acyl substitution reactions. So let us see if we can start our analysis here. So let's look at a mechanism first. So using arrows to show electron movement, propose a reasonable mechanism for this reaction. So let's analyze this first. And whenever you ask for a mechanism, remember we're not supplying here additional reagents. We're just using arrows to show how bonds are formed and how bonds are broken. Using arrows only to show how we go from reactant using these reagents here to give our products. So let's do the analysis. It would appear that there's a bond formed between this carbon and this carbon right here. So for that to happen, we would need to convert these hydrogens here, or extract those hydrogens to form the enolate, a good nucleophile that can react with this electrophilic carbon, and this becomes our leaving group over here. So that's what needs to happen. I've described this here verbally, so you can just read that through. But when you're asked to write a mechanism, please do not give me or answer the question using sentences. This is just our initial observation and analysis. What is required is using arrows to show what happened. So as chemists, that is the way we communicate. We communicate by symbols, by arrows, etc. Not too many words. So here's what happened. So the base, which is a very strong base, abstracts the alpha hydrogen, or one of the alpha hydrogen. These bonding electrons now become our nucleophile, or our nucleophilic region of the molecule. This then reacts with the electrophilic carbon. As you can tell, the electrons will go onto the oxygen, a tetrahedral intermediate. These electrons come back in, and this OET leaves as OET negative. Notice you may say this is contradictory because I just said that OET is a very poor leaving group, but in the presence of a very strong base, and typically these reactions are done in heat, we can get it to go. So when this comes back in, this leaves, and this is the final product here. So again, this is a mechanism question which asks for students to use arrows, as we've seen here, to explain how bonds are made and how bonds are broken. A mechanism. This question here is a synthesis question. Now you have to supply reagents using the information that we have discussed on the previous slides. So let's see if we can look at what should happen here. Starting with ethane. So you went in the lab and you got a bottle of ethane. Ethane is a gas, so you got a cylinder of ethane, for example. And your boss asked you to produce this as the final product. That's the product that's needed for sale. How do you carry out this synthesis here? So first, as I said, we're chemists, so we have to, we're scientists, so we have to have a systematic approach. My suggestion is observation and retrosynthesis. So retrosynthesis means you start by looking at the product molecule. One giveaway here is that this is a tertiary alcohol, and we know that tertiary alcohols can be made by substitution reactions of an ester. Another giveaway is that these two groups here are the same. Two ethyl groups are the same, and they can come from a Grignard reagent. So again, I want you guys to really appreciate the connection between what was done before and the application here. Now we're asking you, can you recognize, or did you recognize, that these two groups are the same, and here's a tertiary alcohol, and we can do a very similar reaction as we have done before to make this compound. All we need is, how do we go from this ethane into a Grignard? That is a process, or the series of reactions is one that we have done before. So let's see what that would be. So, starting with ethane, we do a free radical substitution using chlorine. Why chlorine and not bromine? Because we need not be selective here, because these 6 hydrogens are the same, equivalent. So we have here our chloroethane. We have here the Grignard in the presence of ether to give the Grignard reaction. This type reaction is called an oxidative addition, which we'll see in the next couple chapters. But the main reaction here that you're familiar with is the reaction of an alkyl halide, in this case a chloride, with magnesium in the presence of the solvent ether to give our Grignard reagent. This Grignard reagent reacting with this ester, notice this is the ester, here's our leaving group here, and we have an excess of this. After hydrolysis, this CH2 here will be introduced twice. And of course we have here our tertiary alcohol. Okay, so once again, I want you to really appreciate the connection between the reactions that we've covered and its application. How do you use these reactions to solve problems? I think this is the last slide. Yes, it is the last slide. So, in concluding, I just want to remind us here that we're scientists. We come up with creative solutions for problems. And believe it or not, the tools and information and process that we're using to solve problems in organic chemistry, the same process will be used to solve problems on a larger scale when you start working. So continue to study hard and continue to get the connection between the concepts that we've studied and their applications to solve problems. Okay?